Hello, everyone, and welcome to Notes on 1.7, Transformation of Functions. I know it's a little confusing whenever I do this. I switch up the sections, but I really feel like 1.7 has some valuable things to teach you that then you'll know them before you get to 1.6. So I hate to go out of order, but I really feel like this is the best way to do it. All right, so transformation of functions. Many functions have graphs that are simple transformations of the parent graphs we learned in previous sections. There are two types of transformations, rigid and non-rigid. Rigid transformations include horizontal shifts, vertical shifts, and reflections. Non-rigid transformations include horizontal stretch and shrink and vertical stretch and shrink. So the main way to know what a graph is going to do is where the extra number is. Meaning, if there's an extra number, let's just call it c, at the end of a function, that's going to move the function up or down. Up if c is positive, down if c is negative. But if it's actually part of the function, inside the actual function, the squaring function, the square root function, then it's going to move it left or right. So you might see something that looks like this. It's not part of the square, so it would move it up. But if you saw it here, where the 2 is part of the whole squaring function, that's going to move it to the left. So the up and down is as you would think it is. A plus goes up, a minus goes down. It is backwards from what people are used to, or what you would expect it to be for a horizontal shift. If it's minus c, it's actually going to the right. And if it's plus c, it's actually going to the left. So I do want you to have a bunch of parent graphs in your appendix, or if you're in honors, memorized. So when you think x cubed, you should be thinking, I'm going to graph the parent function, x cubed every time, 0, 0, 1, 1, negative 1, negative 1. And if you have enough room to do it, 2, 4, 6, 8, we do, then 2, 8, and 2, negative 8. We don't always have enough room to reach 8 if it's a little graph, but when we do, we can. Okay, let's do that again. F of x is equal to x cubed, 0, 0, 1, 1, negative 1, negative 1. And then if you can reach it, 2, 8, and negative 2, negative 8. That's the parent graph. The reason that that's so great to have memorized is because, I didn't actually mean to undo that, is because then the shifting part becomes very easy. What I wanted to do was erase that little extra marks down there. So I'm going to switch my color here to red, and I'm going to graph this. Because the 1 is on the outside, that's actually going to move it down 1. So I'm going to take the center point, my 0, 0, and I'm going to pretend that that is 0, 0. It's my new 0, 0. And from there, I know that the graph goes 1, 1, negative 1, negative 1, and from here over 2, up 8. Now you might be thinking, so from here over 2, down 8. You might be thinking, can I just take each point and move it down? Yes, you absolutely can always draw the parent graph and then physically move each point down. But eventually, your goal is not going to have to be to draw the parent graph, to be able to do it without that. So this is how it would look when you've moved the graph down 1. Okay? So to show you exactly what I mean, I'm actually going to erase this function and just move the origin. So this is going to go to the left. Remember, opposite of what you think it is. Usually plus means right, but we're going to go left 2 and up 1 to make a new origin. This is like a trick. It's not really the new origin. So I'm going to go left 2 and up 1. And then from there, I'm going to think about my basic points. Okay? So this is my pretend 0, 0. Okay? So from there, I'm going to go up 1, over 1, and then down 1, minus 1. And then, like I said, if you can ever get 2, you might want to put a little x so you don't get the 3 points confused. From there, over 2, up 8. And from here, over 2, down 8. And then you can draw it. So you don't really need the parent function, but you need to know the parent function. So if you're in CP, you should definitely have an appendix full of graphs with all the parent functions. But the great thing about complicated functions like this is if you know the parent function, you can just shift that origin and recreate it, which I think is easier than drawing the blue parent function first and actually physically moving each point. A family of functions is a group of functions that share the same shape, but are at different locations in the plane. So all of these graphs, both red ones and the blue one, are part of a family of functions. They haven't changed how they look. They're all x cubed graphs. They've just been moved around a little bit. And that is not what I wanted to do. There we go. Reflections in the coordinate axis of the graph of y is equal to f of x are represented as follows. Reflections in the x-axis are going to have a negative in front of the function, and reflections in the y-axis are going to have a negative inside the actual function. So you guys have actually been doing this for a long time, so I'm going to give you an example that you can probably relate to. This is the graph of y is equal to x squared. So if you put a negative in front of it, it flips it upside down. Flips upside down. But what they're going to call it is a reflection in the x-axis. That is the same thing as flipping it upside down. So when you see a negative out in front, that's what it's going to do. If it's a reflection in the y-axis, it'll actually be part of the function. And we'll get to an example like that. On this one hasn't been reflected. It's still the x squared graph, but it's been moved up 2. Now, the way I know that the 2 is going to go on the outside is because it's just up. If it had been x plus 2 squared, that would have meant move left. That would have meant move left, which we don't want to do. Okay, so this is the answer. You can try the next 2 on your own and see if you can figure them out, but I am going to show you. That is going to be my policy, is to tell you when you should pause, but make sure that I'm here to help you. So this next one has been moved to the right, but not up or down. It's still at the same height as a normal parabola. So whenever you want to indicate that something's been moved left or right, it actually goes inside the function. So instead of x squared, it's going to be x, in this case, minus 3. Remember that it's minus, opposite of what you might think when you're going to the right. Last one, hope you tried it on your own, has been moved up 4, so its new origin is up 4, hasn't gone left or right, but then it's been flipped upside down. So I'm going to put a minus in front to indicate that it was flipped upside down. So another graph that I want you to have memorized is the graph of the square root of x. We did do this in section 1.2, but I'm going to quick do it again. The points that I want you to know by heart or at least on your appendix, is 0, 0, 1, 1, 4, 2. And if you're wondering how I got those, I literally just have the table memorized. So if x is 0, then y is the square root of 0, so 0, 0. If x is 1, y is the square root of 1, so 1, 1. And I jumped all the way to 4 because I don't know the square root of 2. But I do know the square root of 4. So when x is 4, y is the square root of 4, which is 2. So those are your basic points. If you have those points memorized, all you have to do is find the new origin and then go left, right, up, down, or flip. So on this one, there's no shifting. It hasn't gone left, right, up, or down, so it's still 0, 0. But it is negative. So instead of going up 1, 1, I'm going to go down. And instead of going to 4, up 2, I'm going to go to 4, 2 like that. And that would be negative. And again, the technical name for it is to reflect over the x-axis. So don't draw this on your paper. I'm going to erase it in a second. Okay? But it reflects over the x-axis. Most kids just say it flips upside down, but the correct terminology is that it reflects over the x-axis. You don't have to draw that on your own paper if it's going to clutter your graph, but I wanted you to see it. Okay. Okay, so just to give you some steps, number 1, you need to know the shape and the parent graph points. So as soon as you see a problem, you have to look at that and say, oh, square root. I know what that's going to look like. I know that's going to be 0, 0, 1, 1, 4, 2. Having this information in your head is going to be so helpful. Second, you need to find the new origin by shifting. So for me, I look at this one and say, oh, this one's going to go back 4 and then down 2. Back 4 and down 2. Remember, not plus 4 and minus 2, back 4 and minus 2. So that's my new origin. If that minus wasn't there, I could just go 1, 1. So I pretend that that's my new 0, 0. And then I do 1, 1, 4, 2. But this one has a negative. So since it has a negative, I'm going to do exactly what I just did on the other one. I'm going to reflect it, but it doesn't get reflected over the x-axis, over where it's been shifted to. If this is my new 0, 0, then this is my new x-axis, so to speak. But I'm going to erase that because that's not actually there. So I'm going to pretend that's my new 0, 0, and then I'm going to go 1, 1, and then 4, 2. If you had to make another point, we actually probably could fit another point. The next one I know the square root of is 9 at 9, 3. Normally I can't fit 9, but since I moved so far over, I actually can. And it would be right there. That point is not really 9, 3. It's 9 over from my origin. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then down 3. So when the negative is inside the function, that's going to flip it over the y-axis. So normally, so this has no shifting, so it's still at 0, 0. But instead of doing 1, 1, it's going to do negative 1, 1. And instead of 4, 2, it's going to do negative 4, 2. It's going to flip this way. I highly recommend checking with a table. I just can't even tell you how important this is. I love, love, love to teach you guys the shortcuts. I love to say to you, think about what this graph is going to look like. But in the end, you should always check a point. So for example, this point is the point 5, comma, 1, 2, 3, 4, 5, 5. 5, negative 5. I would love to know if that was really on that h of x. So to check, I can literally say negative 5 needs to be equal to negative 5 plus 4 minus 2. Negative 5 is equal to negative square root of 9 minus 2. Negative 5 is equal to negative 3 minus 2. Yes. If you just check one point and you actually get the answer that you think you are, then you can feel really confident that this is right. And some people are going to check and some people aren't. Not everybody makes me as happy as a teacher as I want them to. But I will tell you, if you're only going to check some of them, check the ones where the negative's on the inside. Those are the ones that most students get wrong. So I would just check this point. You've finished your graph. You think negative 4, positive 2 is on there. Just plug that in. 2 is equal to the square root of negative 4. 2 is equal to the square root of 4. Yes, it only took a second to do it. But people get this wrong all the time. So take a minute and check. Again, you should try the next one on your own and stop the video, but I will do it. This one is going to get moved up 3. So that's my new origin, and it's going to get flipped. So from my new origin, there's my 1, 1, and there's my 4, 2. I feel like I understand this concept, but I think to myself, could it hurt me to check this point? This point is negative 1, 1, 2, 3, 4. Negative 1, 4. This is not that hard to plug in. 4 is equal to the square root of negative 1 plus 3. 4 is equal to, so this becomes positive. The square root of 1 is 1. 1 plus 3. I feel confident I did it right. I'm going to hand in a quiz. I'm going to get a 10. All right, 2 more. Again, I can't stress enough. I would love for you to pause the video instead of just watching me do it. See if you can get these 2 right on your own. So on these next 2, since this 2 is inside the square root, that's going to affect left and right. So I'm going to go to the left 2, and that's my new origin. A negative on the outside flips it down. So 1, 1, and then 1, 2, 3, 4, 2. I used all my rules, but I am going to quick check. That point right there is 2, negative 2. So I'm going to plug that in. Negative 2 goes in the f of x, right? In this case, k of x is equal to negative, and then the x goes right there, 2 plus 2. Look at that. It just took me a second to check it. Negative 2 is equal to negative 2. I feel good. On this next one, I look at it and I say, oh, the 2's on the inside, so it's going to move it. The 2 is positive, so it's going to move it left, and then it's going to flip backwards because it's a negative x. So I move 2 to the left, and then I flip it backwards. 1, 1, 1, 2, 3, 4, 2. And I feel good about it. Oh, I can't feel good about it. I didn't check. Always check. So according to you, the point 1, 2, 3, negative 3, 1 should be on there. Time me. It only takes a couple seconds to check, not even a minute. 2 minus a minus 3. 1 is equal to the square. Uh-oh. Did not work, right? So there's going to be tricky ones that look like they don't follow the rules, but that's not true. Everything follows the rules. That's why I'm a math teacher. I love rules. Rules are good, okay? But the reason that this one didn't work is because it wasn't in the exact right format. It actually is negative x plus 2, and that negative affects the whole thing. In order for it to flip, it actually affects the entire thing. So it must have originally been this. And if you're thinking, I never would have thought of that, this just got too hard all of a sudden. It didn't get too hard. I don't expect you to think of that. I expect you, when you get a problem that you can't do, I expect you to make a table. Whenever you get stuck, make a table, because you're not going to think of that negative there. So you make a table and you think to yourself, what could I plug in there? And it's going to be challenging. If you plug in a 0, you're going to get the square root of 2. You can't graph that. So pick a number that you can do. You say, oh, well, if I plug in a 1, then I'll get the square root of 2 minus 1. I can do that. When I plug in a 2, I get the square root of 2 minus 2, which is 0. I know the square root of 0. And then, well, I can't plug in a 3 or a 4 or a 5. Oh, you might think, oh, if I plug in a 6, I'll get 2 minus 6. Oh, that's the square root of negative 4. Well, sorry, I got a low battery warning. This is going to happen every day. You can't do the square root of negative 4. So this graph is never going to reach 6. So let's just do the ones that we have so far. We know 1, 1, and we know 2, 0. That's probably not enough for you to make a sketch, except that you knew it moved 2, and you thought it moved left. It actually moved right. 1, 2, 3, 4, 2. It went that way. It actually moved 2 to the right. And you knew that it didn't ever hit 6, that it went in the opposite direction. This is an example of a problem that's making pre-calculus much harder than algebra 2. I never would have given this to you in algebra 2. This is a question that's saying, hey, it's not enough to just know your basics anymore. You have to be able to know the rules, but also think. Again, if you only have 2 and you think that you can figure out this pattern, just try this point. This point is negative 2, 2. So when you plug in a negative 2, what do you get? 2 minus a minus 2, which is 2 plus 2, which is 4, 2. That did work. You literally can hand in a quiz and say, I am positive I got 100 on it because I did that. All right, non-rigid transformations are those that cause a distortion. So your book has this whole way of talking about vertical stretch, vertical shrink, horizontal stretch, horizontal shrink. That's actually not how I do it. I feel like over the years I've found a better way that seems to work better for students. So I'm gonna show that to you, but then I'm gonna just teach it to you by example because I think that that'll work better. So absolute value graph, just going over all the basics. So I'm gonna put the absolute value graph in red. It's a V. As soon as you see absolute value, I hope you're thinking V. If you're thinking, I don't know my parent graphs yet, if you're in CP, you should have a really awesome appendix by your side at all times. If you're in honors, you need to have them all memorized. You can do it. I have faith in you. So when I personally get one of these graphs, my first step is always to make a table. Instead of just in your head, I literally say to myself, 0, 0, 1, 1, 2, 2, 3, 3. And then for absolute value, then it goes negative 1, 1, negative 2, 2, negative 3, 3. I know that's a lot of things on the table, but you should be able to make it fast because you have this one memorized. And this table can be on your appendix. So for every graph and parent function, you can have the corresponding table if that helps you. And then when I want to do h of x, I see it's just 3 times the absolute value. So I literally cross every single one of these off and I multiply by 3. Okay, so h of x is 3 times the absolute value of x. I just cross them all off and I multiply by 3. And then I plot those points. So 0, 0, 1, 3, 2, 6. I'm not even going to get to the 3, 9. Negative 1, 3, negative 2, 6. There's my h of x. Okay. If I had been given g of x, I would have started with the exact same table. Always start with the red table. So I say to myself, all right, for an absolute value graph, it's 0, 0, 1, 1, 2, 2, 3, 3. It's good to do the negatives for the absolute value graph because it makes a V. And if you only do the first couple points, you'll think that it makes a line, which it doesn't. Now, G of x is 1/3 these numbers. So I cross them all off as I multiply by a third. 1/3 times 0 is still 0. 1/3 times 1 is 1/3. 1/3 times 2 is 2/3. Oh, good. Here's a good one. 1/3 times 3 is 1. 1/3. 2/3. 1. Now, you might not be able to graph every point, but you can graph the nice ones. So 0, 0, and then 3, 1. Okay. I mean, you could graph 1/3 and then 2/3, but it's a little tricky. Now, for absolute graphs only, this will not help you with cubics, quartics, square roots. It won't help you with any other thing. But for absolute value only, that number in front is slope. A is equal to the slope. So once you get the 1/3, you can keep going up 1/3. And then on this side, up 1/3, up 1/3. And you can draw a nice line. Remember, absolute value only. Okay? Let's do another one. If you think you got it and you want to try this one without me and then just look at the answer, fast forward in the video, I would love that. So x squared, your parent graph, 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. That's the parent graph. I either have it memorized or have it on your appendix. 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. So how do I do h of x? H of x is 2x squared. I'm just going to multiply all those numbers by 2. So I'm going to cross these off times 2, times 2, times 2, times 2, times 2. So 0, 0, 1, 2, 2, 8. Can't even reach it. I kind of missed that point there. Maybe I should go back. All right, I'm going to tell you something a little fussy. So you can't reach 2, 8. Let's just say that you were a little sloppy with this and you graphed the black line. Let's say you graphed this, 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 and then you just kind of went like that, right? If you're sloppy and your point doesn't actually hit the 2, 8, then I will take off. In other words, if you hit 2, 6, see how this is going to end up hitting 2, 6? 2, 6 is not one of the points. So it's going to seem a little bit strange, but erase those. When you do this, you have to make sure that when you get to the line x is equal to 2, you're still before it because it doesn't actually reach until 2, 8. A little bit tricky there. Okay, so now I want to do the green one. Okay. Oop, that's not green. Now I'm going to do the green one, g of x. But I had it on red because I was going to make the table again. Always start with the table. 0, 0, 1, 1, 2, 4, negative 1, 1. If you're thinking this is too much work, then why did you take precalculus? It's a lot of work. So g of x is equal to 1/2 x squared. You divide them all in half. Half of 0 is still 0. 1/2, 2, 1/2, 2. So at 1, I'm only at 1/2. At 2, I'm at 2. At negative 1, I'm at 1/2. At 2, I'm at 2. I look at that and I think I might have been able to go a little further. So at 3, it would be 9. How did I get that? Because on the parent graph, it's just x squared. So x squared. And half of that would have been 4.5. Let's see if that's worth it. 1, 2, 3, 1, 2, 3, 4 and a half. And then it's symmetric. So yeah, it might make you, not on your homework, but on a quiz or a test, if you're trying to make a nice graph, that would be a good idea. So this method is not how it's probably done in a textbook if you're reading along in your textbook, but I really like it. And I have found that kids are very successful with this. Make the parent table, cross things off. Very, very successful method. Evaluate each of the following. So this is the greatest integer, function. What it means is if you were traveling along the number line and you reached 1, 2, 3, 4. So I'm traveling along the number line and I get right there, 1.2. What is the greatest integer? Oh, I guess you need to know what an integer is. In case you don't know what an integer is the set of whole numbers and their opposites. So these are integers. So pretty much 0, 1, 2, 3, 4, 5, 6, and then all the negative ones. So I'm sitting here traveling along the number line, always from left to right, and I get to 1.2. And what is the greatest integer I've passed? It's 1. So the greatest integer of 1.2 is 1. And you might be thinking, what possible use could this have? Well, ironically, that's actually how we do birthdays. It's a very real life thing. So when you are 16 and 2 months and somebody says, how old are you? You, in your head, use the greatest integer function. You don't say, I'm 16.3 months old, or I'm 16 and 8 months old. You just say, I'm 16. And when do you say that? You say that literally until your 17th birthday. There's something funny about it, but even if you're only 1 day away, you still can't say you're 17. You can say, I'm almost 17, but you're not actually 17 until the day you reach 17. And it's the same thing with this. The greatest integer of 1.9 is still 1. The greatest integer of 1.9999999 is 1. If you're on the number line and you keep getting closer to 2 until you're actually at 2, the greatest integer is 1. So one year, some kid said to me, you should call it the birthday function. So I do like to refer to it as the birthday function, but you won't see that online. That's not like a national thing. That's just me here at South. So if you're actually at 3 on the number line, 1, 2, 3, then the greatest integer you've reached is 3. If you're at 2.8 on the number line, so you've been going along, you get to 2.8. What was the greatest integer you passed? 2. Or you could just think of it as the birthday rule. On your 3rd birthday, you're 3. When you're 2.8 years old, you tell people you're 2. Let's go down to this one. When you're 12.4 years old, you tell people you're 12. I love the birthday function. Whoever thought of that name, I feel bad I don't remember the student's name anymore that said it. But the one bad thing about it is it doesn't work for negatives because we don't have negative birthdays. So negatives are tricky. Make sure you pay extra close attention. They do the opposite of what you think that they would do. So if you're at, I'm gonna have to add some more lines here because I can't reach them. If you're at negative 1, 2, 3, 4, 5, you're at negative 4.5. The question is, what did you reach on your way there? The greatest integer you reached is actually negative 5. You never reached negative 4. So you can't say that this is like, oh, I just take off the decimal and there's the answer. It doesn't work that way. If you're at negative 7, then you've reached negative 7. Integers are fine. Now, you're not always going to be making a number line, but if you want to, you can make a little piece of one. Negative 18, negative 17, negative 16, negative 15. If you're here at negative 16.3, as you're traveling up the number line to reach that number, what's the greatest integer you've passed? Negative 17. That is the greatest integer function. And it has its own special, just like square root functions and things have a special little symbol. This is the symbol, or I've seen it in some books as a double set of parentheses. And actually your calculator doesn't have that symbol. So your calculator does INTX to represent greatest integer function. Let's make its graph. So I like to think about it as the birthday function. So here you are, you're born, 0 years old. You stay 0 all the way until the day you turn 1. That's an open circle, and on that day you get to jump up to 1 year old. And then you stay 1 year old until you're 1.5, 1 3/4. And then on the day you turn 2, you get to jump up and say, I'm 2. So the answers, if you look back at the last page, the answers are always regular numbers. There's no y values that are decimals. And that's why the graph looks this way. When you're 2, 2 1/4, 2.5, and then the day you turn 3, you get to jump up to being 3. I know this is getting a little boring, so let's just fill the rest of them in. And then remember I said negatives were tricky. You can fill in the negatives just by following the pattern. So there you've learned a new function, the greatest integer function. This was actually introduced in section 1.6. So I actually am doing just a little bit of section 1.6 here. It follows all the same rules that we've already learned. Every function all year is going to follow all the same rules. I love that about math. So I'm literally going to take my birthday function and I'm going to move it up 2. That's my new 0, 0. And then I'm going to make it. Okay? Up 2. I go in the other direction. And that's what it looks like. Sometimes kids get lazy on a quiz and they say, do I really have to fill in the whole thing? Yes, you have to fill in the whole thing. That only took 20 seconds. You can do it. Answer in your own head while you're listening to this video. How does that move? Up, down, left, or right? Hopefully you said right 3. 1, 2, 3. So I start here. That's my new 0, 0. And I make my birthday function. Now, somebody who really loves math is going to be very clever and say, hold on, that graph could have been, f of x could have been down 3, and wouldn't that have actually given you the exact same answer? In this case, it would have, okay? And in this case, moving it left 2 would have. So the greatest integer function is interesting in that it has some little quirks, but you should just follow the rules, okay? It'll make your life easier if you just stick with what you know. But if you made that observation, good for you. All right, this is going to get a little bit harder now. This is literally a super challenging problem. We didn't do this yet, but let's make the Let's make the chart. So normally we make a chart 0, 0. When you turn 1, you're 1. When you turn 2, you're 2. But the greatest integer function only is easy to graph if you graph something in the middle. So when you're 1.5, you're still 1. When you're, oh, that's not where I should have put that. So when you're, say, 0.7, you're still 0. When you're 1.5, you're still 1. When you're 2.3, you're still 2. You really are going to want to have some extra numbers in this besides just the integers. Otherwise, you won't be able to graph it. So now when you multiply those all by 2 times 2, times 2 is equal to 0, times 2 is equal to 0, times 2 is equal to 2, 2, 4, 4. Now graph these, and you'll see it right away. So 0 is still going to be 0, 0.7 is still going to be 0, but at 1, it jumps up to 2. And then hopefully that's enough to make you see the line. At 1.5, it's still at 2. But then at 2, it jumps up to 4. So make this is just 1 point. You have to make the whole entire line. And then hopefully at that point, you can see what interesting thing it's doing. But if you're not sure, plot more points. But I would plot them on your black XY table for the parent function and then just multiply everything by 2. I think you'll be more successful that way. All right, last one. We're almost done, everybody. Thanks for hanging in there with me. So now we have a negative out front. It is going to flip it upside down. And you're welcome to use the rules. You're welcome to just say, hold on, that doesn't flip because it stays the same. But then normally it would be here, so I'm going to put it here. And then go for it. But before you draw all of them, you probably want to check a point. I can't stress this enough. If you're not checking and you get it wrong, don't come crying to me. So according to you, this point right there is 1, 2, let's say 2.5 looks like it goes with -2. So let's try that. When you put a -2 goes in for f of x, negative greatest integer of 2.5. The greatest integer of 2.5 is just 2, and it's negative. So I feel good about that. Okay, the rules are there to help you make those connections, but you should still check because sometimes, when we did one earlier, sometimes things are a little wonky and they don't go quite the way you think that they would. All right, great job on these notes, everybody. Have a super day.